In 12 days, a 33 billion-ton interstellar visitor called 3I Atlas will plunge past our star at 80 times the speed of a bullet. And that's where things could go wrong. Its path is nearly aligned with the solar system plane, something no random comet should do, raising the disturbing question: is this a natural wanderer or a machine designed to break at our star and stop within our solar system? While Earth's eyes will be blinded by our star itself, the only thing we'll know for certain is what emerges on the other side. The real danger lies in what we won't see when it matters most, a path that defies the odds. Atlas rockets toward our star at nearly 55 km/s, following a path that defies probability, like a car entering perfectly into the right lane of a cosmic highway. Instead of diving from a steep random angle, it glides through the solar system plane tilted just 5 degrees from the ecliptic, the invisible disk where planets orbit like a spinning coin in the air. For an interstellar space visitor, this is a statistical outlier. Random arrivals should spread across the sky, most missing the ecliptic by wide margins like balls thrown from all directions. Yet here the trajectory nearly overlaps the planetary lanes as if mapped to blend with local traffic, like a driver who perfectly knows the traffic rules of a foreign city. Orbital simulations by planetary scientists show that only a minuscule fraction of interstellar objects should arrive this way. The ecliptic covers a thin slice of the celestial sphere. For a comet to approach within 5 degrees is like throwing a dart at a spinning globe and hitting a city street. Technically possible, but statistically nearly impossible. The last two interstellar objects, Oumuamua and Borisov, came from high inclinations, their paths cutting through the solar system at sharp angles like planes flying too high or too low. Atlas, in contrast, traces a retrograde arc moving against the planetary current, but nearly flat along the disk, like swimming against the current but at the water's surface. This alignment isn't just a curiosity. It changes what's possible at perihelion, the closest point to our star. An object approaching along the ecliptic meets our star at a shallow angle, maximizing the window for any maneuver that leverages solar gravity, like a skateboarder using a ramp to gain extra speed. If a spacecraft designer wanted to use the Oberth effect, a way to amplify a rocket burn by timing it for maximum speed near our star, this is the geometry they would choose. But the numbers alone are enough to raise eyebrows. Discovered on July 1, 2025, by the Atlas survey in Chile, Atlas is only the third confirmed interstellar object. Its entry velocity of over 200,000 km/h confirms it's not bound to our star, like a visitor who clearly isn't from the neighborhood. Perihelion comes on October 29, 2025, at a distance of 1.36 astronomical units, just inside Mars' orbit, like passing between two moving cars on a highway. For now, orbital mechanics says it should slingshot and disappear forever. However, the strange alignment of the trajectory with the ecliptic, along with its hyperbolic velocity, leaves a persistent question. Is this cosmic chance, or the signature of intention? As the clock counts down to perihelion, the stakes rise. If Atlas is natural, it's a rare but explainable visitor. If not, the geometry alone suggests a level of planning and purpose that goes far beyond chance. The moment of truth, Oberth effect. At perihelion, Atlas will be moving at nearly 68 km/s, more than double the speed of the fastest spacecraft ever launched from Earth, like a cosmic cannonball. This is the moment when the laws of orbital mechanics offer a unique loophole. The Oberth effect, first described by Hermann Oberth in 1929, states that a rocket burn is much more effective when performed at high speed within a gravitational well. Simply put, the same push from a rocket engine does much more when the object is moving faster, especially near a massive body like our star, like hammering with full force instead of just tapping. The principle can be summarized in a simple rule. The change in orbital energy from a burn is proportional to the object's velocity at the moment of the burn. If a spacecraft fires its engines while crawling through deep space, it gets only a modest energy boost, like pushing a parked car. But fire those same engines while passing our star at 68 km/s, and the effect multiplies, like pushing a car that's already moving at high speed. A 1 km/s change in velocity at that speed translates to a dramatic alteration of the object's trajectory. The math is clear. Kinetic energy increases with the square of velocity. So a burn at perihelion is like swinging a hammer with full force, not just gently tapping. For Atlas, the theoretical path to capture would require deceleration, what engineers call a retrograde. Burn right at closest approach. The goal would be to lose enough velocity to change from a hyperbolic escape trajectory to a closed orbit bound around our star, like braking a high-speed car to enter a parking space. Calculations show that to fall into a permanent solar orbit at 1.36 astronomical units, the object would need to lose about 20 km/s at perihelion. That's a huge ask. Even for the most efficient chemical or nuclear propulsion known, the amount of fuel required would approach the object's own mass, like a car that needs to carry its own weight in gasoline. However, the Oberth effect is the only way to make such a maneuver remotely plausible with any known technology. Natural comets experience outgassing jets of vapor and dust that can nudge their paths, but these forces are weak, chaotic, and rarely aligned with orbital needs. They might change a comet's velocity by a few meters per second, not tens of kilometers, like the difference between being pushed by a breeze versus a hurricane. A controlled, precisely timed retrograde burn at perihelion would stand out in the data. The resulting change in trajectory would be obvious to astronomers tracking its path after solar conjunction. The telltale sign: a sudden step-like drop in exit velocity far beyond what outgassing can explain, like a car that suddenly slows down for no apparent reason. That's why the perihelion window matters. If Atlas attempted deceleration, our star's gravity would act as the amplifier, turning a modest push into a major transformation. The mechanics are straightforward. The energy stakes immense. What remains is watching for any sign that nature, or something else, has the means and intention to use them. The great blackout begins. From mid-October through early November 2025, Atlas disappears behind our star from Earth's perspective, like an actor exiting the stage at the most important moment of the play. This isn't bad luck. It's the result of a fixed rule in astronomical observation, like a law of physics that can't be broken. When a target falls below about 30 degrees from our star, all major ground-based telescopes are forced to look away, like being unable to stare directly into a spotlight. Avoiding our star isn't just about protecting sensitive optics from blinding light. It's a safety protocol built into hardware and software, like automatic brakes in a car. The blackout window, extending from October 22nd to November 7th, means that as Atlas races through perihelion, no direct images or spectra can be collected from Earth. Space observatories face the same limits. The Hubble and James Webb telescopes are programmed to never point within 50 to 85 degrees of our star, eliminating any chance of a last-minute peak. Even TESS, with its wide-field cameras, is blocked by solar elongation rules, like having to close your eyes when the light is too bright. The Parker Solar Probe and Solar Orbiter, both designed for close solar studies, are pointed at our star and rarely risk deviating off-axis. Their instruments are optimized for plasma and magnetic fields, not faint objects at the edge of their fields of view, like using a microscope to try to see the moon. Mars orbiters, briefly better positioned, attempted risky snapshots as Atlas grazed past in early October, but the object was 50,000 times fainter than their usual targets. Preliminary images from the ExoMars Trace Gas Orbiter were dismissed by the ESA team as likely noise, like trying to photograph a candle in a snowstorm. No confirmed detections were released. For now, the only certainty is absence, like trying to watch a movie with the screen turned off. A multi-week period when any dramatic change, natural or otherwise, could occur unobserved. When the object reappears near dawn in November, astronomers will be looking for after-the-fact evidence, piecing together what happened in the dark. Brightness should be an indicator of mass. For Atlas, that assumption is now under fire, like discovering that a person who looks large actually weighs nothing. Photometric readings calibrated against standard comet reflectivity place the object's mass at about 33 billion tons, which would make it one of the heaviest natural visitors in recent memory. However, when planetary dynamicists ran the numbers after the Mars flyby on October 3rd, the result was silence, like throwing a stone into a lake and seeing no ripples. At a distance of just 29 million kilometers, a body of that size should have nudged Mars's orbit, or at least appeared as a small anomaly in orbiter navigation data. Instead, the Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter reported no measurable perturbation, like a giant truck passing without making the ground shake.